Hello everyone, here we are ready to do our experiment 9B post-lab calculations. So this is a titration with a pH meter. You guys have already come across titration, you have done titrations in Chem 1 and you remember that we put an indicator to find the end point. But the difference here is we're not going to be using an indicator. Instead, we're going to monitor the pH of the solution and then we're going to draw a graph, and from the graph we're going to find out what is the end point of the titration. So the first one that you are performing is a titration between a strong acid and a strong base. Our strong acid is hydrochloric acid 0.1 molar, and then the strong base is 0.1 molar sodium hydroxide. Okay, so you are planning to take about 25 milliliters of hydrochloric acid, and then you're going to be adding sodium hydroxide in the increments given in the first column. And then as you increase the sodium hydroxide, we're going to check to see what is the pH after addition of these amounts of milliliters of sodium hydroxide. So to begin with, volume of the second reagent added 0, meaning you have not added any sodium hydroxide, you have only hydrochloric acid. You check the pH 1.43, which makes sense because hydrochloric acid is an acid and it needs to be a lower pH. And then you add 5 milliliters, you swirl the flask and get the pH 1.45. So you're going to be adding first 5 milliliters increments until you come to 20 and record the pH. And then from 21 to 30, you're going to be adding 1 milliliters increments. And you can see that at 25, pH 3.19, and addition of 1 milliliter, 26. You see the big jump, 3.19 goes to 10.72. And then you can again, after it jumps, then we know that is the region that the end point has happened. Okay, but we don't know yet what is the end point. We have to draw a graph. And then you're going to be adding again 1 milliliter increments up to 30, and then from 30 to 50 you're adding 5 milliliters increments, and then measure the pH of the solution. So at the end, all the acid has been reacted with the sodium hydroxide, so your pH is going to be basic. You can see it is in from 10 to 12 it increases. Okay. Similarly, we are performing a titration between a weak acid and a strong base. So the weak acid we are using here is acetic acid. We keep the weak acid in the flask. Again, you can see weak acid acidity is less than a strong acid. So that's why before any sodium hydroxide is being added, at the very first reading, at 0 volume added sodium hydroxide, pH is 3.08. Because it's a weak acid, it has a higher pH compared to as a strong acid, hydrochloric acid, 1.43. So we are keep on adding again sodium hydroxide up to 20 in 5 milliliters increments, and then from 20 to 30 you're going to be adding 1 milliliter increments. Okay, so you can see the pH increases 3, 4, 5, 6 and 10. So between 6 and 10 there are 4 pH unit changes difference. So that is where the end point happens. Little bit basic side, since we are with a weak acid, and then as we keep on increasing the sodium hydroxide, you can see end point reaches and then the solution become basic. Now your goal after you see this data, after you watch your virtual video, what you need to do is you need to draw these with these two sets of data. You need to draw a graph on Excel, not the handwritten one. Use Excel. All of you have access to Excel. So go ahead and draw a graph of volume of second reagent added, which is your first column, versus the pH. And then likewise you need to draw two graphs. Okay, after you draw the graphs, then only you will be able to answer these questions. Titration A endpoint pH, and then the titration B endpoint pH, pKa or pKb for the titration B, and then from the pKa or the pKb you can find out the Ka or the Kb. And the question 4, why no K asks for titration A. Now question 2 and 3 asking pKa or pKb, that's based on titration B, not for A. Why we don't ask K, acid dissociation constant, for titration A? That's because it's a strong acid and a strong base, so they dissociate 100%. It's not a partially dissociation. So once you put a strong acid and a strong base, you will not find any ions intact. They will be completely dissociated to give you separate ions. Whereas a weak acid or a weak base, it is partially dissociated. You will also find undissociated acid or undissociated base. So for those we can um, write and find the K, which is acid dissociation constant, because it's a partial dissociation, whereas a strong acid, strong base, there are no K. Okay, so you can explain that for question number 4. Now, I drew two graphs for these two titrations, but though they are my graphs, you cannot copy my one. I want you guys to go ahead and draw your own Excel graphs for these two titrations. So let me show you how the graphs would look like. Okay, let's go ahead and open up our Excel, this one. Okay, so what you're going to do, it's not that clear. So you go to your Excel. On the first axis, that's going to be your x-axis, you're going to be writing down the volume of the second reagent added, and then the y-axis, you're going to be putting down the pH, and then you're going to draw a graph between x-axis excuse me, between the volume of the added base and the pH of the solution. Like this. Okay, so when you draw a graph, you want to make sure that the graph needs to have a title, and also axis needed to be labeled, volume of the added base in milliliters and the pH of the solution. Excuse me. So your first graph, you will see a graph like that. And then how do you find the end point? So you need to find out what is the end point of the graph once you draw it. So from here to here is going to be the middle of that, going to be the end point. Okay, so you select the midpoint somewhere here. So you draw a straight line where you find the midpoint, and then you draw a line from here to your x-axis. That's the volume. If you do that, you can find out what is the volume that needed. You don't need that information. Only you need to know what is this value in terms of pH. So strong acid, strong base, the neutralization or the end point happens right at pH 7. So if you once you draw your graph, you will see that is at pH 7. So end point. You will get this information from the graph that you're going to draw. Okay, and for the second one, you also need to draw putting the x-axis data as the volume of the sodium hydroxide added, y-axis is going to be the pH of the solution. So when you draw it like that, you will see your graph similar to this. Again, you need to have a title of the graph, and then the axis needed to be labeled, and then you will see that the pH, the initial pH started somewhere here, and then it's gonna gradually increases, and then from here to here you have to figure out what is the midpoint between these two. That is where the end point of the weak acid strong base. So that's between 8 and 9, right? So you can figure that out, maybe 8.7, something like that. Okay, pH of the end point between a weak acid and a strong base. And you also need to find out what is the pKa of the solution. Now you see this area here, this, since we are at a weak base, that is the buffer region. What is the buffer? Buffer region is, now let's say we have acetic acid, HA. I'm going to represent HA as our acetic acid with water. We can have H plus, H3O plus A minus. So in this region we can see pH changes gradually because you are in the buffer region. So when you add the base hydroxide ion, so the base OH minus is going to react with the A minus and form, no, hydroxide ion is going to react with HA. Okay, I did a mistake. OH minus is not going to react with A minus. Hydroxide is a base, so the hydroxide ions, when you add, it's going to react with acid and form water plus A minus. Okay, so you can see the first part, that's the buffer region here, the one that I have circled in the graph. So if you find the midpoint over here between this graph, somewhere here, and then you find what is the pH of the midpoint, that is basically is the pKa of the solution, pKa of the weak acid. Remember the Henderson-Hasselbalch equation? Henderson-Hasselbalch equation is pH equals pKa plus log conjugate base over conjugate acid. Now at this point, the concentration of base and the concentration of acid are going to be equal. Okay, at that point, so then the pH will become equal to pKa. So if you find the midpoint between this gradual increased buffer region, that will give you the pKa. So after you draw the graph, you figure out what is this pKa. It's going to be less than 5, maybe it's going to be 4.5 pKa. Okay, again, don't depend on my number, you draw your own graph, pKa 4.5, and then you need to find out what is the Ka, and you guys know how to find Ka, don't you? So Ka, remember the equation for the pKa? pKa equals negative log of Ka. So Ka going to be 10 base, if you find it 4.5, negative 4.5. So you can find that. And you need to write down that information in your data sheet for your calculations. Okay, so that's how you're going to answer the questions. It's a short lab, right? And let me show you something else. Here in this graph, weak acid strong base titration. So the first one, this one over here, let's say this part over here, this one right here, this one is the strong acid strong base titration curve, and then the weak acid, the other one is the weak acid weak acid strong base titration. You can see, so this one is titrating propionic acid, but we did acetic acid. They both are very much similar. Propionic acid, pH is little high to begin with. Okay, so you can see pH is bit higher to begin with over here, around 3. And then remember, this is the buffer region that I talked about. So at that point, HPR equals PR minus, which in other words, acetic acid concentration is similar to the acetate ion. Remember, I told you in our case, HA concentration equal to A minus. Conjugated acid and the base, so they are the same in the buffer region. So you find the midpoint, and then once you find the pH at that point, which is going to be the pKa. Okay, and it explains this graph also, as you add the base, how the pH changes. And then to find out the end point, you find out what is the midpoint between these 2 points, and then you find out the pH of the solution at the end point. Okay, that's all you have to do, and then gradually pH increases since we're adding pH. So these are the graphs for strong acid strong base titration curve and weak acid strong base titration curves. And we also got the similar graphs, right, for our two titrations when I drew it, and you guys will also get similar titration curves like this. You can either do two separate titration curves like that, or you can do it on the same one. So you will see the difference between the strong acid strong base and the weak acid weak base. It doesn't matter, but somehow I want you guys to draw these graphs on Excel and then answer the questions based on the graphs. Okay, I believe that's all you need to answer. Okay, so here titration A endpoint, titration B endpoint, and then for the titration B, pKa, we are not going to have pKb. pKb is for a weak base, but we use pKa because it's a weak acid. So you find out the pKa the way I showed you, and then Ka you can find out using the equation pKa equals negative log of Ka. So you can find out the Ka. Why no chaos for titration A, which I explained earlier. So that's all you need to do for this experiment. Okay then, bye-bye.